Thank you. Hi, everyone. I hope you're enjoying your lunch. So for the next few minutes, I'm going to ask the following question: foundational models for generative computational design. How can we build that? Do we need large neural nets, data, or something else? And I'm Ferdous. I'm a postdoc working with Faiz Ahmed at MIT, and I'm also an incoming assistant professor at George W. Woodruff School of Mechanical Engineering at Georgia Tech. So my PhD advisor taught me that in academia, we don't really have a lot of surprise, so I should not hold out information. So I'll give the answer to the question immediately. The answer is all of the above. We need large neural nets, we also need data, and we also need something else. But before I dive into this, it starts with representation. And what I mean by that, if you think about one-dimensional data like time series or two-dimensional data like images, we have a pretty good idea of how to represent this data for our specific use cases. But it becomes very difficult for three-dimensional use cases. Mesh is perhaps the most popular and widely adopted 3D data representation technique for 3D shape, to be more specific. But what about mechanical shapes? If we want to represent something like this, it's a commercial robotic gripper from a company called Robotic with a Q. It costs around $5,000 to $7,000. It's fairly complex and highly precise, so mesh is not a really good representation for this type of 3D shape. It has a lot of components too. And which brings us to the question of what is a good representation for 3D shape for mechanical applications, for manufacturing applications, and engineering applications in general. And if you think about it, we need mainly three things to work with this type of 3D shape representation. It needs to be precise, it needs to support constraints, and it also needs to support the topology that we are thinking of. Historically, we have been working with mesh, point cloud, voxels, or boundary representation, or BREFs. And unlike other type of data representation, BREFs has some benefits. They are not dependent on the resolution, and there is no loss of information, but it comes at the cost of a really complex data structure. It's a very hierarchical data structure that is very difficult to work with. If you're working with a neural network, they're very difficult to extract information from. But this has been the industry standard for computer-aided design for more than 3 decades. And one good thing about that is we can represent the 3D shape as a parametric design, which is really handy for our applications. Now, I want to introduce two different types of representation for the same 3D shape. Instead of BREP, we can actually represent a 3D shape as a piece of code. It can be a CAD program. And what is a CAD program? A CAD program is a sequence of CAD modeling operations with the parameters that you have. And this is pretty much what you're doing in the UI of your CAD software that is encoded as a piece of program. Or we can directly convert the 3D shape into a piece of Python code or a C++ code. For example, there are open source libraries like CAD query or different type of scripting language, even for commercial CAD software, that we can use to represent a 3D shape. There are two major benefits to this. They are interpretable. You can actually see how we created the design, and the entire design intent is preserved because you have access to the entire design history, the parametric design history. And also, they're editable. It is very difficult to edit a mesh or a voxel, but unlike that, you can take this CAD program, pass it through a CAD kernel, and create the 3D shape and modify in any way you want in your favorite CAD software. So how do we learn to generate CAD or 3D shape based on this type of representation? So here's some of our very recent work that came out last year. It's called GenCAD and GenCAD 3D that can take image or sketch as input or mesh or point cloud as input and create the 3D shape. But unlike STL or mesh type generation, what we're doing, we are creating the 3D shape step by step from scratch. So you have access to the entire design history. We are not merely creating the final 3D shape. We're creating pretty much everything that generated this design. How we are doing that? It goes back to the representation that we used. We used the CAD program representation to do that, and it allows us to enable this sort of generation of 3D shape. If you think for a second, what we are doing by representing the 3D shape as a CAD program, we can represent the parameters as a vectorized representation. So now you have all these tokens, the operations like arcs, lines, extrusions, all these tokens, and their vectorized representation, which basically converts them into a language modeling problem. So we have converted the 3D shape generation problem into a language modeling problem like natural language processing, and we can use all the benefits of large language models and these type of architectures. And if we take this input, pass it through a geometry kernel that the field and the researchers have built over the last few decades, which are tremendously robust and have been supporting the entire industry and community, and we can pass it through this geometry kernel and create the shape step by step from pretty much from scratch. Does it work? I think it's a little bit hard to see the sketches, so because maybe some monitoring issue. So in summary, it works fairly well and you can see the complexity of the shapes that we have based on the data set that we used. And one of the major limitations, we don't have access to a more complex data set. And if we have that, the method is fairly general, and we believe that it's fairly scalable based on the access to a highly complex data set. And there's one other benefit that I want to show you. We 3D printed some of the shapes from the test data set that has never been shown to the model during training. 3D scanned the shape using a commercial software, commercial scanner, and our model can generate a diverse range of shapes from this point cloud input. And again, the benefit is that you can take any of the samples created and modify it the way that you want using your favorite CAD software. And finally, we asked the following question. Instead of relying on CAD program, why not directly take a foundation model from image and text and try to fine-tune it so that it understands 3D shape? And that is pretty much what we did. Given an image or sketch and text as input, it can create directly the Python scripting code of the 3D shape. Here's a demo of that project. This is from the test data set. We took a photo with an iPhone camera of the 3D printed object, and our vision language model can create Python code of that 3D shape, and we can execute that code, get the underlying 3D representation, modify it the way that we want. So it's pretty much very flexible and customizable. And finally, I want to show you this piece of work that has been very recently accepted at NeurIPS this year. We wanted to encode how humans learn or design something using interface. Human engineers pretty much use a CAD interface, and the CAD interface is very complex. If you have worked with CAD software, you probably know that it has thousands of buttons. So we wanted to understand how do we build AI model that can mimic sort of humans to design something from an image or some type of conditional input. But to do that, we need a data set. But unfortunately, there is no such data set in existence. So we made our own data set. It's a collection of 41,000 annotated video recordings of CAD UI interface and creating a 3D shape. This is one single data point from the data shape once on video of how we are trying to encode how humans design into a representation. So in this case, we are no longer using the intermediate representation. We are directly trying to encode how humans design. And here's the interesting part. We actually compared it to computer games and web-based application, and you can see the complexity in human 3D design. The user interface elements are like 6 to 7 times, and we also have to think about the 3D reasoning that does not really come into play for generic web applications. So it's a very hard task and very difficult to solve. And if you're interested in this sort of work, feel free to check out our work. Okay, so I'm almost at the end, so I'll finish with how I think all these things tie together to build sort of like an universal intelligent design system. How many of you have used Copilot here? No, pretty much a lot. So Copilot is, I find it really fascinating. I can have like a really complex code base, and I can ask it, the Copilot, to check whether any error in my code. It can go ahead and find out there are 4 mistakes in my code, fix that mistake, and give me a report of what the mistakes it's being made. Can we do that for engineering design? Sort of like a Copilot, but really intelligent design system. And my view of this is that we need to have AI model, generative AI model that can synthesize 3D shape, that can verify 3D shape, and that can also optimize 3D shape as well. But in addition to that, we need AI models that can reason about 3D shape. So it can understand what to put screws or threads, things like that, and also that can manipulate 3D shape just like human cognition would, how we would rotate a shape and how we would interact with the 3D shape to understand it. So that's pretty much my hope, that with this, a new generation of foundation model would be brought into existence. So with that, I'll finish my talk, and thank you so much for listening.
So before we do the changeover, maybe you can spend about 1 to 2 minutes for quick questions. So if anyone has questions for Dr. Alam, please go ahead.
CAD models, thanks for the presentation. You can create a CAD model in different ways. You can sketch it, one can extrude, and you can have 2 sketches to a track. How do you count, what are your measures for the different possible ways to model components?
If I understand the question correctly, so how do we ensure that we follow a specific way, or?
Well, you can model a part in different ways.
Yeah, of course.
So, but are you using unique,
No, so we are using a diffusion model in the backend. So the hope is that even there's like multiple modality of creating the same object, it will be captured by the data distribution. If there are like 2 ways to create the same design, we will be able to